Earlier, we have discussed how histone tails can be post-translationally modified to alter chromatin compaction and access to the DNA. This video provides an introduction to histone deacetylases, or HDACs, the enzymes that remove acetyl groups from histones. As we have discussed previously for other marks, the mechanisms governing epigenetic marks such as histone acetylation can be summarized by the writer, eraser, and reader model. For histone acetylation, the writer proteins are histone acetyltransferases, the eraser molecules are histone deacetylases, and the reader molecules are bromodomain-containing proteins. Here we will focus on the erasers, the histone deacetylases. HDACs remove acetyl groups from histone proteins. Sometimes they are now called KDACs, which stands for lysine deacetylase, because many HDACs also have non-histone substrates. Generally, HDACs are divided into 4 classes, and they can require a number of cofactors for enzymatic activity. This table provides an overview of the 4 classes of HDACs. Class 1 includes HDAC1 and RPD3, 2 well-studied HDACs which function in most tissues. Class 2 includes several more tissue-specific HDACs. Class 3 HDACs are the sirtuins, proteins similar to SIR2 from yeast. SIR2 stands for Silent Information Regulator 2. As in yeast, in the absence of SIR2, sequences that are normally silent and inaccessible to transcription are now expressed because failure to remove acetyl groups maintains DNA in a more accessible, less compacted state. Class 4 is defined by human HDAC11. HDACs in Class 1, 2, and 4 are considered classical HDACs. They require a zinc ion for catalytic function, and they can be inhibited by the drug trichostatin A. Class 3 HDACs, on the other hand, are not affected by trichostatin A and are dependent on NAD+ instead of zinc. The proteins in this class also have mono-ADP ribosyl transferase activity in addition to the deacetylase activity. Like the various histone acetyltransferases and the bromodomain reader proteins, the various HDACs differ in their specificity. Many HDACs are able to recognize and deacetylate more than one acetylation site. For example, SIRT1 deacetylates H3K9, H3K14, H3K56, and H4K16. In addition to target sites on histones, many HDACs have non-histone targets as well. Clearly defining target site preferences for HDACs and other chromatin modifiers is often difficult, as they are assayed in isolation in vitro studies, but function as part of large protein complexes in vivo. HDAC activity in most cases is impacted by its protein binding partners, and the formation of large HDAC complexes is important for activity. This is illustrated in the diagram to the right, where HDAC1, HDAC2, and HDAC3 have low activity when they're studied in isolation, but show high activity if they're together with their protein partners. HDAC1 and HDAC2 are also part of several different complexes. In addition, post-translational modification of the HDACs, such as biphosphorylation, is sometimes required for activity, as shown in Part B of the diagram. Lastly, some HDACs, especially those in Class 3, are shuttled between the cytoplasm and the nucleus, thus regulating their activity. The most obvious consequences of recruiting an HDAC to a specific site in the chromatin is the removal of acetyl groups from the histones. However, there are other consequences as well. Lysines are not only modified by acetylation, but also by a variety of other modifications such as methylation. Removing an acetyl group makes the lysine available for a different modification. In addition, some modifications inhibit or promote the modification at neighboring amino acids, so other modifications in the histone tail might be affected as well. Also, the protein complexes that HDACs form often include other histone-modifying enzymes, so that recruitment of an HDAC might lead to the modification of another nearby site. This crosstalk between different modifications makes it more difficult to predict the outcome of recruiting an HDAC to a locus in terms of chromatin compaction and accessibility. In terms of its impact on transcription, recruitment of HDACs most often leads to transcriptional repression. First, removal of the acetyl groups leads to an increase in positive charge of the histones and a strengthening of the interaction with the DNA, leading to more compaction. Histones lacking acetyl groups also recruit repressor proteins that are unable to bind acetylated histones. In addition, unacetylated histones are unable to bind transcriptional activators that bind only to acetylated histones. In addition to these direct impacts of the removal of acetyl groups, HDACs also impact transcription due to their crosstalk with other histone modifications as discussed in the previous slide. In summary, we have seen that HDACs are the eraser molecule that removes acetyl groups from histones. There are 4 classes of HDACs, 3 of which are dependent on a zinc ion for function, while the other class is dependent on NAD+. Substate specificity and activity of the HDACs is variable and often depends on protein partners and post-translational modification of the HDAC. Recruitment of HDACs typically leads to transcriptional repression, partially because of the tightening of the binding between histones and DNA due to the removal of negative charges on the histone, partially due to the indirect impact on other post-translational modifications on the histones.